So the last thing we were talking about was, I believe, electrolytes, yes?
Yep.
We had talked about the three different types of electrolytes. We have strong, weak, and non. And at this point in time, the most important of the strong electrolytes are the soluble ionic compounds. So anything that you remember the solubility rules, we're going to get into them again today soon. Any ionic compound that you put in water that dissolves is a strong electrolyte and will conduct an electric current very strongly. That's also going to be true of compounds called strong acids. Other compounds that dissolve but are not ionic are non-electrolytes. They will not conduct an electric current well. And the in-between case are the weak electrolytes. So a weak electrolyte solution, if we look at these pictures right here, might have a very small concentration of ions in them. And that small concentration of ions is just enough to conduct a slight current. And so if we test with a light bulb, as you were seeing right here, this is very poorly lighting up. That's indicating there's a lot of resistance ultimately between those electrodes, and it's not conducting electricity very well. So that's what we would see with a weak electrolyte. Most importantly right now is to focus on the strong electrolytes and the non-electrolytes. The weak we get into more as we go a little bit further into the class. Okay, so the strong acids, the word strong means must be a strong electrolyte. Strong acids are compounds which completely dissociate in solution. Okay, and there are 6 of them, and I will stick to my guns on that. There are 6 in this class and in 140. When we get into more advanced classes, we might see that we can add a whole new broad category of acids, and we even eventually get a class of compounds called superacids, which make these things look paltry by comparison, but we're not going to worry about those guys. So for our inorganic standard acids, these are them: hydrochloric acid, nitric acid, sulfuric acid, and then hydrobromic, hydroiodic, and perchloric. All of these break up and produce ions in solution. All of them lose the H plus at the front. Okay, hold on one second here. I want to go ahead and go to my notes. So let me open up my notes so we can continue a little bit further. But what I would like you to do is write reactions, at least for the first 2 of those, showing how they dissociate in solution. Why did that get closed? Chapter 4 lecture. Good. 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 Okay, so bottom of page 4-1 on the notes. Okay, you can now see the notes, correct?
Yes.
Yes? Good.
Yeah.
Okay, so dissociate means again that they are going to break up into ions. So hydrochloric acid would be the easiest one. Well, and nitric. And AQ means dissolved in water. Okay? This means, and I'm actually going to do something weird here and use an equal sign instead of an equation. This means what? When we see an aqueous strong acid, that means in the water is H plus and chloride ions. The same thing for nitric acid. Since this is a strong electrolyte, we've written H plus AQ plus NO3 minus. If it were up to me, I would rewrite all of this and come up with a whole new symbol that looked like this. Because what I'm trying to show is that in water, hence the little waves, this is what you get, okay? I don't really want to call that a chemical reaction. Because people could debate that honestly and say, is that really a chemical reaction? It's hard to say. Now, the last one is one that I do need you to understand. There are two protons. In water, only the first one is predominantly removed. That would leave behind the bisulfate ion. Not to go too far into the definition, but this thing right here, the bisulfate ion, is a weak acid, meaning that it only partially dissociates. So if we were to take a picture of reality, sulfuric acid in water is mostly bisulfate ion with protons. But is there some sulfate ion according to this? Yes, it does partially dissociate. How much? That's a question we answer in chapter 14 in Chem 140 tomorrow. If anyone wants to see the video, I'll be happy to share it with you. Okay? But for right now, we're just going to say that this is really what it does. I know I'm going into a little bit of detail with that, but I want to be very clear. This is all in water only. In water only. When we go ahead and add this to an aqueous base solution, which is still water, sodium hydroxide, which is a base, will be happy to rip that hydrogen right off, okay? This is in neutral water. That's all I'm saying right now for that, okay? The hydrogen mostly stays there. And guess what? Even all this isn't honest. I have actually been lying about all that. Well, I've been telling a very convenient lie that chemists like to tell themselves to keep the symbolism nice. And that is, in reality, every time I wrote H plus up here, that really wasn't right, okay? We call these protons, not hydrogen ion. Well, we can call them hydrogen ions, but we like to call them protons. In reality, those protons jump onto water molecules. They don't just float around in space, well, in the water on their own. They attach themselves to water, which we said was very polar. And they've actually formed these things called hydronium ions, H3O+. Each water molecule doesn't really want to hold on to that extra H+. So those hydrogen ions, the H pluses, are constantly being passed around back and forth. It's like a game of hot potato. Imagine someone literally throws at you a potato that's extremely hot. And you don't like that person, and you don't like people in general. You'll throw it to another person. Otherwise, you throw it on the floor. But you don't like people. So you're going to take the potato and hand it to someone else who will burn themselves, and then they'll hand it back. You get the idea. It's the same thing with an H plus ion. None of the water molecules necessarily want to hold it at any point in time. They just constantly get passed around. And so whether we really call it an H plus ion or whether we really call it a hydronium ion, it's really a matter of taste, so to speak. Even though hydronium is more true, it turns out in a lot of contexts, it's much easier to just say H plus. But then in our heads, we know that it's really riding around on an H3O+. The reason why that's easier is because what would we always have to include in the balanced equation if we're using H3O+? We'd always have to throw in an extra water molecule. And that can get annoying. It can start adding confusion to the balanced equations. And so rather than doing that, we usually will leave it out. And so I will prefer to write H+, except in contexts where it's better to write H3O+. Okay. Are we all okay with that? Are we all okay with that little deception that stays between you and me and all your other chemistry professors? Yes. Very good. Okay. So, strong bases. Strong bases really shouldn't be thought of totally as a different category. Strong bases are still soluble ionic compounds. Okay. They are just soluble hydroxides. That's all it is. They are the soluble hydroxides. And if you remember your solubility rules, which we'll review again in a moment, all the group 1 compounds are soluble in water, correct? So that means sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium hydroxide, cesium hydroxide. All of those are strong bases. They're all soluble bases. In addition, we generally all agree that barium hydroxide is a strong base. And most people agree strontium hydroxide is a strong base. Calcium hydroxide, on the other hand, is a bit controversial. Okay. You might run into the mad wandering chemist who yells at you and says, no, it's not a strong base. Well, don't argue with them. It's not worth it, okay? But there are some people who would say it's not. And let me explain. When we get into measuring how soluble something is, the group 1 ones are all much more soluble than the group 2 ones. Like, for example, it's easy to form a high molarity solution of sodium hydroxide. Barium hydroxide, you can add it. It still very much dissociates, but it does max out at a much lower molarity than these guys do up here. Okay, and I know I haven't technically introduced the term molarity, but you've had Chem 120, you should generally know what I'm talking about. Okay, so we'll consider all of those to be strong bases. Note what is not on the list. From group 2, who seemed to have gotten left out?
Radium?
Yeah, but that's, we don't talk about him. Okay. Who else? Who very common got left off the list? Above calcium?
Magnesium.
Magnesium, good. Yeah, magnesium hydroxide is not a strong base. And there's no controversy about that. I don't know anyone who would call it a strong base. It's called in a solution milk of magnesia, which we take for stomach ache. Okay, you would never drink sodium hydroxide for a stomach ache. It would kill you. It would destroy your esophageal, not esophageal. Yeah, esophageal. It would destroy your esophageal tissue as it goes down. It would be horrible. So don't ever do that. Magnesium hydroxide is a weak base, which makes it great for treating sour stomach. Also, aluminum hydroxide. Aluminum hydroxide, anyone know the brand name of that? That is called Malox. Have you ever heard of Malox? At the store, that's aluminum hydroxide. All right. The weak electrolytes, the only ones we really deal with are weak acids and weak bases. I want you to think of it this way. If there's any other acid that we talked about in this class, and it wasn't on the list of the 6 strong, it's weak. Okay? That's not strictly true, but anything that we're going to talk about, if it's not on that list of the 6 strong, it is weak. Some people would say, well, chloric acid is kind of, no. Chloric was not on the list, only hydrochloric. So therefore, we wouldn't consider that to be a strong acid. It's very borderline. They only slightly dissociate, and that means they don't let go of their hydrogen. Did I have a picture of that? I can't remember. No, I did not. Okay. But they mostly hold on to their hydrogen ion and therefore are going to be weak. Of the weak bases, the only really important one right now is ammonia. And we will look at that a little bit more as we go further in the class. And then the non-electrolytes, as I said, are compounds which are not going to form ions, even though they do dissolve in water. They are primarily things which are able to hydrogen bond, okay? And we'll review hydrogen bonding later in the semester, but if you remember it from the end of Chem 120, you would know that alcohols can hydrogen bond. That is, you have a hydrogen on an oxygen. This would be very attracted to water. So this dissolves, but how many ions does it make in water? If it's a non-electrolyte, it makes
0.
0 ions, yeah. So this compound is a non-electrolyte. Isopropyl alcohol, non-electrolyte. Sugars, which are things that end in ose, glucose, sucrose, they all are non-electrolytes. They dissolve in water, but they don't make ions, okay? They're all held together by covalent bonds. Okay, now we move into the really, really big topic. And let me be blunt about this topic. It's a do or die topic. To make it through this class and to make it through next semester, you have to be a master of this topic. There's just no way around it. You have to focus on this. You can't say, well, I'll eventually get good at this. You need to focus on this topic probably more than any other topic until you can do the calculations upside down, up, you know, literally before you go to bed, first thing you wake up in the morning. And that's going to be molarity calculations. Okay, because they're just so pervasive in chemistry, so ubiquitous. Anyway, concentration is going to tell you the amount of solute in a given amount of solution. Or in some cases, there's a thing called molarity that we talked about in chapter 11. It would be the amount of solvent. But for right now, amount of solution, okay? So we're just going to focus on molarity in this chapter, and in chapter 11, we'll add a few more concentration terms. And it is defined, and you must remember the definition, it needs to be etched in your brain, as moles of solute per liter of solution. Note what term does not appear in that definition? The word solvent, okay? It is moles of solute per liter of solution. That is the solvent plus the solute. And we abbreviate this with a capital M, usually italicized. Moles of solute per liter of solution, okay? Let it sink in. Don't forget that. The worst thing as a professor that I can say about this is that M, as convenient as it is, it leads students astray all the time. What do you think people see when they see the M incorrectly? What are they going to see? They're only going to see the moles part, okay? And they forget about the liters part. So you must remember, even though we see an M, that's not 1 unit, that's 2 units. Moles over liters of solution, okay?
Would it be incorrect if we were to write it M over liters?
M over liters?
On a test or something?
Yes,
Yeah.
M over liters would be incorrect because M is meters. MOL over liter is perfectly fine, okay? Also, don't ever abbreviate molecule as MOL. It needs to be, anything other than MOL or MOLE, because those mean moles. Okay. All of the solutions that we deal with in lab, for which we see the molarity, are prepared in a very special way. And it's important to understand how they're prepared so that you can really understand the process here. Let's say here that I have a solid solute and I want to make a solution. Let's make life really easy. This container, called a volumetric flask, there's many of them, and they are designed to measure only one volume, very, very specifically. Let's make life really easy and say that that's a 1 liter volumetric flask. Okay? Let's also make life easy, and let's suppose that that's 1 mole of a compound. Okay? So let's say that's 1 mole of a compound, and this thing is 1 liter flask. So you add water. You actually wouldn't add the wash bottle till the end. You'd just get this probably from a beaker. So you pour in water, and then you add just enough water to get to that line right there, okay? And that would be exactly 1 liter. Anything over and the solution is ruined, okay? Because you have added too much water. You can't just pour some out because you'd be pouring out some of the solute along with the solution. Okay, so this was again a 1 liter flask. That is the 1 liter mark. Vitally important question right now. How much solvent did I add in this process? What volume?
Can you repeat the question?
Yes, I can repeat the question. And actually, let me change the question a bit. I'm going to go ahead and change it into a poll. So let me ask you a question here. So we said that it was a 1 liter volumetric flask, correct?
Yeah.
So my question here is the following, okay? How much water was added to the flask? One liter. Some other amount. Okay. And let me see, I've never done this polling thing before. So, oops. Did it come up, the poll?
No, not yet.
No, it did not. Okay, hold on 1 second. I don't think I like some of these features yet. Okay, now
There
it
it
should
is.
up, right?
Yeah.
Yes.
Okay, so again, remember that the marking on the volumetric flask, that's a 1 liter mark. Okay, so how much water was added to the flask? A liter or some other amount of water? Okay, I'll give you another 20 seconds to respond. And here we go. Okay. So you can see the results right now.
Yeah.
Good. Does anyone want to argue why they picked 1 liter?
Because the container is designed to hold a liter.
Very good. The container is designed to hold a liter. That makes sense. Does anyone want to argue for why it might be some other amount?
Well, aren't you mixing it with another solute so that already has like its own volume, and then you're adding water to it to equal 1 liter?
Excellent. Yes and no. The correct answer is probably some other amount. And that is because the solute, if we think about it from the most basic sense, the solute itself might take up some volume, wouldn't it? But you see, technically, it's actually even more tricky than that. In reality, adding a solute often doesn't add volume. It actually takes away volume sometimes, because what sometimes happens, and this depends on the compound, is this. Sometimes when you add a solute, that causes, and you can see the picture right now of the solute in the water.
Yes.
Yeah. Sometimes that actually causes the water molecules to pull in even closer. So with some solutes, you would actually have to add less than a liter. With some solutes, you might actually have to add more than a liter, because as you're adding the water, the solvent particles get pulled in even closer. So the most important thing to get out of this is what? The only thing that we know is at the end we have 1 liter of solvent or 1 liter of solution. What's the only thing we know for sure? At the end we have 1 liter of solvent, 1 liter of solution, or both.
So
1 liter of solution.
Only 1 liter of solution. We don't really know how much water was added, because we don't measure the water as we're adding. We only measure the amount of solution. And that is why this definition is so important. We don't know the volume of solvent that we added. We only know the volume of the solute plus the solvent together. And that's much more convenient for us than trying to say the amount of solvent, because, as I said, sometimes the solute pulls the water in close. Sometimes it might take up more space. We don't know. It depends on the solute. And that would be a real headache if we had to keep changing our minds each time. So what we just say is, what is the volume of the solution? Okay? Does that make sense to everyone?
yes.
And if not, at least are you willing to accept it for right now?
It makes sense.
Yeah.
Maybe.
I'm hoping it does. And, this is actually a lab that we do. When I was going through graduate school at UCI, this is one of the first labs we do, is we have students take 10 milliliters of water and 10 milliliters of another liquid called methanol. Okay, so 10 milliliters of water plus 10 milliliters of methanol. What is the total volume? 19.9. No matter how much you try, it's not 20. Okay, so what is that suggesting happens when you put water and methanol together? They are doing what to each other? They start to pull each other closer, and they take up less volume. So what do we have a law of conservation of? We have a law of conservation of mass, right? So the mass of the methanol and the mass of the water, they add together. No problem there. We do not have a law of conservation of volume. Okay? The only time you can absolutely say that the volumes will add is when you're adding identical things. So 20 milliliters of water plus 20 milliliters of water will always give you 40 milliliters of water. That's not a question. But 20 milliliters of water plus 20 milliliters of isopropyl alcohol, you can't be so sure, okay? It will be very close to 40, but it won't be exactly. So that's a vitally important thing to be careful about with solutions. You cannot assume that the volumes will add unless it's the same solvent. Like, for example, I could take sodium chloride in water, potassium chloride in water, put those together, they'll pretty much add without a problem. Very unlikely to run into a problem there. But they have to be the same solvent. Otherwise, you can't assume that they'll add. Okay. So let's take a look at some problems here. So let's start with the easiest type of a problem, which is we want to find the molarity of something where we're dissolving 150 grams of KOH in enough water to make 2.500 liters of solution. Please note the wording. That's a very important wording. It sounds very inexact, and there's a reason. I did not say add 150 grams to 2.500 liters of water. I said I add it to enough water so that I end up with 2.500 liters. Okay. So how do I find this? I need, what, two things?
The moles of the KOH.
Excellent. I need the moles of the KOH. And I need the
liters of
the volume. Yeah, in liters. Well, we already have that. That is
2.5.
yeah, excellent. 2.500 liters. Okay. Oh, is that pole still gone? Okay, there it is. Good. And how do we find the moles of potassium hydroxide? That is, we just do a conversion. So I've got 150 grams. And you can see everything I'm writing at this point, correct?
Yes.
Good.
Is it possible that you could zoom in just a little?
For you, absolutely. How's that?
Perfect.
Okay. Can I go out just a bit? Is that okay right there?
Yes, thank you.
Okay, sure, not a problem. And please, that's definitely something you should interrupt about. And I don't want to use that word interrupt. That's something you should definitely stop me over. If you can't see the screen, I won't get annoyed about that at all. I will get annoyed if you send me an email from an email address where your name is like, you know, Squeaky G or something. I need to know your name. hence the announcement today. Okay, no one did that to me, but do please. I don't know if students realize this, but we do gossip about you all, and well, not you individually, but we say, my God, this student I got today. They emailed saying, "Hi, I'm in your class. What time is class?" And it's like, okay, this instructor's teaching 5 classes, you know, I'm in your class, what time's your class? And then they don't write their name on top of it. So it's like, you know, so just don't be that way. Anyway, I got 56.11. I don't know why that bothers me, but did you all get that as well?
Yeah.
What's that? A little louder?
Oh, I got 56.108.
Okay.
I used more decimal places.
Yeah, I rounded because the other ones have potassium only goes out to the hundredths. Same with oxygen. Okay, but I thought it was a different value for some reason. I think I'm thinking of sodium. Okay, so we've got 150 divided by 56.11. And I get 2.673. 3. Good. So the molarity is? 2.673 moles. Over 2.500 liters of the solution. And the molarity I get is 1.069. Which is conveniently rewritten as 1.069 molar. Okay. Life is usually not this easy because most of the solutions we deal with, we're not usually going to be measuring in liters. We're usually going to be measuring in milliliters. So there is a conversion step that might get involved in that. And usually we're working with smaller amounts. So often you have numbers that are in scientific notation. Oh no. But yeah, that does happen a lot. Okay. Suppose the question had been instead, what is the molarity of the solution formed by dissolving 150 grams in 2.500 liters of water? What problems does that introduce? As I've already mentioned, the main problem is
Conversion.
Yeah, well, we don't know what. We don't know the actual.
If the volume will stay the same.
Yeah, we don't know if the volume of the solution will stay the same exactly. Okay, so we cannot solve it as written. May I make a slight amendment to that question? And don't write this down unless you really want to somewhere else. What if the question had been written this way? 150 grams of KOH in 2.5 liters of water. What's the difference? It's a lot less significant digits, right? If I'm okay not having more than one or two significant digits, I could probably do that. And why is that okay? The difference here is what? Going back to chapter 1, where is my uncertainty in this problem? Which decimal place am I uncertain about as written?
The ones.
No decimal, the tens. Okay? The last significant digit is the 5. So I'm not even positive about that. I might have 146 grams. I might have 153 grams. I might, remember when we talk about significant digits, that last significant digit is your uncertain digit. How about here? Here I'm uncertain about the tenths. When I do this, I'm only going to get 2 significant digits when I try to find when I work with these. And that might be good enough. If we're only wanting 1 or 2 significant digits in our answer, it would probably be okay to use those values because the amount that the molarity will change is so small. But if you want 4 significant digits, you can't do that. Okay, so that's a minor point. But if you want a lot of significant digits, you have to do it the way I've said here. You have to add it in enough water to make 2.5 liters. If you don't do it the right way, it's probably going to be close enough if you're only doing 1 or 2 significant digits. But again, that's really limiting you in how good your results are. And most work that we do, we don't want 1 or 2 significant digits. We want a lot more than that. So That's why we have to do it this way. Okay, question. What mass of sodium chloride is required to make 750 milliliters of 1.500 molar sodium chloride solution? If you look ahead to chem class, on Mol Mastery, I would like you to do this one quiz really soon. There's a quiz on switching back and forth between milliliters and liters. I know that sounds silly, but you want to be able to do that super fast. It saves you a lot of time in calculations. So if I want to do molarity here, I either want to commit to working all in milliliters or all in liters, and it's much easier to work in liters for right now. What would this be in liters?
7500.
Yeah, good. And in Chem 130, I expect you to be able to make that.
75.
What? Oh, yeah. I expect you to make that transition really, really fast. You just move the decimal 3 to the left, okay? And there you have it. All right, so I want to know what mass of sodium chloride. So what is that? What unit am I probably looking for there? I want
Grams?
sodium chloride. Yeah, good. So how do I solve this? You're given two numbers, the volume and the molarity. Now, I do want you to solve problems on your own, but let me give you one piece of advice, and that is you almost never begin with the molarity. The molarity is a conversion factor. You almost never begin with a density. You almost never begin with a rate. Anything with 2 units should be used as a conversion factor. And that's why this thing, as I said, is a problem. You have to always remember in your head that this is actually 2 units. Moles of sodium chloride for every liter of solution. And I'm sorry to be so obsessive about this, but I just am trying to keep you from making mistakes. Okay, so that means we should start with the volume here. It's certainly possible to solve it starting with the molarity. It just doesn't look very nice. It doesn't logically really make much sense. Okay, so let's start with liters. Of the solution. Good. Now, what do I want to do with the liters of the solution? I want to convert that to
The mass of NaCl?
in a minute, yeah, eventually. But I don't know the mass relationship yet. I know the liters to moles. So yes, definitely mass. But first we need to get to
Moles?
good. So you agree the molarity lets me put the volume down here and the moles of sodium chloride up here.
Correct.
Go where? In front of liters goes a 1. Okay. If you're given the molarity, then that's per 1 liter, per 1 liter. And then the moles would go in the numerator. So that number on the molarity is always with the moles, not the liters. And then to find mass, we just convert from moles to grams using the molar mass, right? So 1 mole of sodium chloride, that's one of the ones I know off the top of my head is 58.44. Just because you use it so much. Okay, so I've got 0.75 times 1.5 times 58.44. is 65.75. Any questions on that? If I reworded the question, if I took 750 milliliters of this solution and I boiled off all the water, would I have this much sodium chloride?
Yes.
Yes. Good. Yes. Yeah. That's basically another way of wording this. You know, if I take away all the water, that's how much sodium chloride is in it. Good. There's another kind of question of that type. How many moles of sodium nitrate are there in 35 milliliters of a 0.9375 sodium nitrate solution? How many grams? Everything is pulling at me to try to teach you how to use millimoles right now, but I'm going to stay away from that. Let's just stay with what we have here. Okay, again, if I'm given molarity, there's a couple tricks I can use if you're given milliliters. Number one, you could change milliliters to liters, right? Or you can always say that 1 liter is the same as 1,000 milliliters and change this to 0.9375 moles for every 1,000 milliliters. Let's just stay with liters though. So although it adds a lot of decimals, what would this be in liters? This would be
0.03500.
Yeah. Promise me you will always double check when you do this. A lot of students will give me 0.35 on that, and that would be wrong. If you think you might make a mistake, write out a full unit conversion. If you think you can do this without ever making mistakes, I recommend just moving the decimal, and it's just faster. Okay, how many moles of sodium nitrate are there then in that volume? We just used the molarity. So I have here 0.03500 liters of solution. And what do I want to put in the denominator? I want to put
1
1 liter.
excellent, 1 liter of solution has
0.9375
0.9375.
moles. Correct? So on this question, I asked you how many moles. So let's see what that gives us. So 0.035 times 0.9375 gives me 0.03281. Moles sodium nitrate. And we can find the grams by multiplying by the molar mass. So let's find the molar mass. 22.99 plus 14.01 plus 48 from the oxygens. I'm getting 85.00. Let's not write it right there. Please double check. I got 85 grams per mole. Anyone else get that?
Yeah.
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 Okay. Very, very good. So if I just have 0.03281 moles, as I said, you just multiply by the molar mass. But if you want to see that with the units, which I wouldn't blame you, 1 mole of sodium nitrate is 85 grams. Good. And I get 2.789 grams. Okay, so any questions so far? No? Okay. All right, the next part is vitally important as well. Okay. Actually, the next 2 parts are critical. This next part, especially for Chem 140, but also we use it this semester as well. And that is, instead of doing molarities of compounds, we're often interested in the molarities of ions. Okay, so this is what we call the ion concentrations. And the way that we find the ion concentration is you basically just multiply the molarity by the number of ions which are in the formula. And that should make sense, because if we think about this, let's say I have aluminum chloride. What is that really in solution? It's a strong electrolyte. So how many aluminum ions would we get when I put this in water? I get a single aluminum ion, which is then surrounded by water molecules, but we can forget that for now, and 3 chloride ions. Does that make sense? Since this is a soluble ionic compound, it all dissociates. So the aluminum ion, and these are 3 separate chloride ions. They aren't bonded together in any way. So they all go their own way. So the important thing to get out of this picture is the following. If I have 1 molecule of aluminum chloride, I don't like to use the word molecule here, but let's just use it for right now. I would get 1 molecule of 1 aluminum ion and 3 chloride ions. Okay. On the other hand, if I have 1 mole, this would give me 1 mole of aluminum and 3 moles of chloride. So in other words, if we were to generalize this, suppose I have AXBY. Let's say this is a cation. Let's say this is an anion. How many X's will I get? I mean, how many A's will I get?
One.
X of them. And how many B's will I get?
Y of them?
Y of them.
Y of them. Yeah. If that makes sense. So how many aluminums did I get? I got 1. It was 1 down there. How many chlorides did I get? That's like Y, right? I got
3.
3 of them. So no matter what, for every 1 mole of AXBY, I'll get X moles of A and Y moles of B in an ideal perfect world. And we'll worry about when it's not ideal later. Okay, so that means that the molarity of anything with a 1 in front will always be the same. So if this is 0.10 molar AlCl3, it's also 0.10 molar in aluminum. And the notation we use for that is we use brackets. We use square brackets. Chloride, though, for every 1 mole of aluminum chloride, we get 3 moles of chloride. So it's always going to be 3 times as great. In a perfect world. Okay, so let's find the concentration of all ions in A and in B. Okay, so think about this now, KOH. When it dissociates, how many potassium ions does it make?
1.
1, good. And how many hydroxides?
1.
1. That's going to be really easy on this one. Since these both have 1 in front of them, the molarity of potassium will be?
It would be 1 to 1, right?
Yeah, it would just be 1 times, 1 to 1 would be if I'm comparing them to each other. And you're correct in what you just said. It's just that's not when we'd use the word 1 to 1. Okay. It's just 1 times 0.945, which is 0.945. Excellent. 1. And then hydroxide, exactly the same thing. What about barium hydroxide? That's a mistake right there, by the way. That should be A. Should be down there. So barium hydroxide?
1 barium and 2 OH.
Very good. So 1 barium and 2 hydroxides. So that means that the molarity of barium is 1 times that molarity. By the way, you don't really need to write 1 times, you know, once you know what you're doing, which is probably now at this point. But the hydroxide, it wouldn't hurt to show that it's 2 times. And 2 times 15 is 30, right? And we don't need to move the decimals around, so 0.030. So often the concentration of an ion will not be the same as the starting solution. And you'll always know that if there's 2 or more of that ion in the formula, as we see. We are making an important assumption right now, one that we'll study more in chapter 11 and see when it's not always true. And the assumption is that a strong electrolyte does what? What's the definition? A strong electrolyte
Dissociates.
completely. Yes, right? Okay. What we'll see in chapter 11 is sometimes there's some hangers on. So maybe occasionally a hydroxide doesn't really want to leave. It's like, no, keep me, don't let me go. You know, and so sometimes we find that these are actually a little bit off. But for right now, we're going to assume that everything is ideal, which means everything goes away completely. And you don't have to worry about that kind of a circumstance just yet. Okay. Now, you know what? I'm going to skip this question and come back to it after I do dilution. I want to do dilution first. So we'll come back to it. There we go. Okay. Now, when we go and we buy chemicals from a chemical supplier, if we know that the chemical is going to be a solution, which is true of all of our strong acids, for example, they're always going to be sold as solutions. We're not going to be able to buy them 100% pure. Then what we get is we buy them as stock solutions. So for example, in our labs, when we buy hydrochloric acid, we buy it and it's labeled as 12 molar. Very nasty stuff. And we call that concentrated hydrochloric acid. Concentrated sulfuric acid is 18 molar. And these are the molarities of other concentrated acids. There's no reason you need to memorize them, so don't worry about them. Okay? Now, in most of our labs, though, we don't want 12 molar or 18 molar. We want much less concentrated. And so to make a solution much less concentrated, we dilute it by adding more solvent to it. Or vice versa, we take it and add it to more solvent. Either way, it ends up with a solution which is diluted. Okay. Another thing that needs to be etched into the brain permanently, make sure you know this without even doing a calculation. Adding solvent to any solution always does what to the molarity? Adding solvent, let's go back to the formula. Adding solvent always increases which one of these? The moles or the liters?
The liters.
Yeah. Adding solvent will always increase the volume. And increasing the denominator does what to the number as a whole?
Decreases the molarity, right?
It decreases it. Very good. So adding solvent always decreases the molarity. Okay? Think about this in real life. You take a soda, you have ice cubes in it. What starts to happen to the taste as the ice cubes melt? It starts to become more and more, for lack of a better word,
Water.
Yeah, watery or diluted, right? Or if one goes to a bar and orders a drink, you know, you can tell it's been diluted because there's less flavor to it. You just don't perceive it as much. Okay, to find the molarity, the moles of, if you're trying to find the molarity of a diluted solution, there's 2 ways. You can find the moles of solute and then divide it by the final volume. Or you can just use this equation right here. So the starting molarity times the starting volume equals the final molarity times the final volume. Let me be very clear about what both of these are saying. What is molarity times volume? Let's say it's liters. Molarity times volume in liters gives you what unit? Moles per liter times liters gives you moles.
Mole.
So the unit on the left is moles. The unit on the right is moles, what this equation is telling you is adding volume does not change the number of moles. It only changes the
Moles.
moles per volume, okay? So the number of moles never changes for the solute. That's very important, because if you're adding water and only water, there's no way you can be getting more moles of the solute. Does that make sense? Right? If you have ocean water, adding more water doesn't change the amount of salt in the ocean water. It only changes the volume. Okay, so 1s represent starting values, 2s represent ending values. We see this kind of notation a lot. Okay. How is this done in principle? In principle, we measure out the amount of chemical that we want. So like, for example, with hydrochloric acid here, we measure out, if we want it really exactly, and it's a really nice even amount, we use what's called a volumetric pipette. A volumetric pipette, which is picture B, is only designed to measure a very specific volume. There'll be a number written on it. For example, it might say 5. If it says 5, that means 5.00 usually. So it gives you the value to a lot of significant digits. And it will tell you just how accurate it is right there. Okay. A graduated pipette is kind of like a graduated cylinder in that you can pick out what volume you want. It's generally more accurate than a graduated cylinder, but not as accurate as a volumetric pipette. The problem with the volumetric pipette, as I said, is it can only measure one volume, whereas a graduate pipette can measure, a wide range of many different volumes. This is the dilution process. So you first use the calculation M1V1 equals M2V2 to figure out how much of the starting solution you need. I'm assuming I already know the molarity of this, and I'm assuming I know how much I'm going to need in the end. Okay, so doing my calculation, I figure out how much I need. I add it to a volumetric flask, and then I dilute with water to the mark. In these cases, it sometimes is okay to add volume. If this has the same solvent as this, in other words, if this is mostly water and this is mostly water, then you can probably get away without adding the volume. Still, this is probably a better way to do it. Okay. Also, this picture is a bit of a lie in that no one would sit there with a wash bottle and do this, because this would take 20 minutes. You would pour it in using a beaker and then add the wash bottle at the end to get the last few drops, and that would be it. All right, so that's dilution. These problems seem to drive people crazy, and I've never really understood why people have such a hard time with these, because it really does just come down to using this equation and having an understanding of just final volumes, starting volumes, things like that. It's really not that hard. Okay. So let's say that a chemist would like to make concentrated acetic acid into a more dilute solution. Okay. So let's say they start off with 25 milliliters of concentrated acetic acid, and they want to dilute it to 1 liter. So I'm going to use the molarity to find it first using the equation and then without the equation. Actually, let's do without the equation first. The equation is no good if you don't understand why it works. Okay, let's label things first, though. What is 25 milliliters? Starting volume or ending volume?
Starting.
Starting volume, good. by the way, you can use any volume unit you want. The rule is, though, that they have to be the same starting and ending unit. So I can leave that as 25 liters, or I can also say that that's 0.0500 liters, okay? I'm proactively making that change because I see over here, this is a volume of 1 liter. What is that right there? That is
Final volume.
final volume. Be extremely careful because I leave traps on these questions. My trap is, did I say that's the final volume, or did I say I added 1 liter? Because if I said I added 1 liter, that's a totally different problem. I said that is the final volume. So that is really V2. If I said I added 1 liter, then what would be the final volume?
1 liter plus the starting volume.
Excellent, yeah. But there's no worry, there's nothing here to say I added it. I diluted it until it was 1 liter. Good. And what's the 17.4, please?
The molarity of starting molarity.
Very good, starting molarity. Good. So let's do this without the equation first. The rule is I'm only adding water. So therefore, the number of moles is constant of solute. So if I start off with my 0.02500 liters of solution, I could be more specific and write starting solution, but we know that every 1 liter of that solution has how many moles of acetic acid in it? The starting solution.
17.4.
Good, 17.4. Okay, so 0.025 times 17.4. It's 0.0435. I'm sorry, 0.435 moles of acetic acid. And then the molarity would be I'm a little bit I'm regretting making V2 1 liter. I'll leave it 1 liter. But it would be 0.435 moles over the volume. The reason I'm regretting that is because it doesn't look like I change anything, which is true. I don't in this case. But if it was 2 liters, if V2 was 2 liters, that would have been 2 liters in the denominator. Do we agree on that? And if this had been 3 liters, that would have been 3 liters. So it just happened to be 1 liters in this problem. And so therefore, the molarity is just 0.435 molar. And that was the point here, that the number of moles didn't change of acetic acid, only the volume. With the equation, because this is a calculation we do so often, it makes sense to have an equation for it. So the equation was M1 V1 equals M2 V2. We are solving for
M2.
M2, excellent. So M2 equals M1 times V1 over V2 so this would be 17.4 molar V1 0.02500 liters over 1 liter. And I would be willing to bet that comes out to 0.435. And the units which cancel are liters over liters. By the way, can you see here if you had used milliliters, that would have been okay? So long as they're both milliliters or both liters or both quarts, whatever they are, so long as they're the same unit, they cancel.
So as long as they're the same unit, it doesn't matter which unit you use, because in the end you end up with the molarity.
Exactly. And for pretty much any kind of formula of this type, so like for example, parts per million is another kind of unit that we could use. You could have used parts per million over parts per million instead of molarity. For pretty much anything other than molality, I don't believe this works for, because that's a little bit different. But for most concentration units, the rule is you can use any concentration units we want. We're just going to do only molarity. And you can use any volume units you want so long as they're the same volumes there, because they cancel. And so that would be 0.435 molar. Always check. Did the number go down? Did the molarity go down when you added the water?
Yes.
Yes, yeah. I get very, very sad if I see the molarity going up, okay? That's a really bad mistake. Don't ever do that, because it just looks really weird. You know, oh, look, I added water and all of a sudden I have stronger acid. No, never works that way, okay? So please be very, very careful to that. This isn't a really practical problem in that you almost never just randomly add chemical in an unknown amount. What do you usually know? You usually know how much you want and how much, what the concentration you want is. So in the real life, you usually know how much you want and what concentration you want. So it's M1 and V1 that you have to find out. M1 is usually because you already bought it from the company at 12 molar or 18 molar or 16 molar. So usually you don't get a choice on M1. So what is the value we usually are finding in the real world? Usually you're finding
The second volume, right? What you need to add?
the first volume.
The first volume.
Yeah, you're saying, all right, I have HCl. I already know it's 12 molar. I know that I need 5 liters of 0.1 molar. And the reason I know this is because there's a book that says I need that amount, if that makes sense. I have so many students, so I need this volume, and I know this is the molarity I need. So these come from the situation. The situation tells you M2 and V2, and M1 is just what you already have in your chemical storehouse. V1 is the thing that you usually have to find in the real world. Okay. So how much water must a chemist add to 30 mLs of a 2.050 molar sodium chloride solution to make a solution which is this way? The wording on this one's a little bit tricky. This is already an aqueous solution. Did I say that? No. Let me be very explicit about that. Meaning it's already in water. So I can add water to it and the volumes add. How much water must a chemist add to 30 mLs to prepare a solution which is 0.1025 molar. Again, this is not a great wording, but let's just do it. Okay, so what do we know? 30 milliliters is what?
The starting volume.
The starting volume. 2.050.
Starting molarity.
What's that? The
Starting.
starting molarity. Good. 1.1025 molar is the
Final.
final molarity, right? So I have enough information here to solve for V2. So I have here M1 times V1 equals M2 times V2. Is V2 equals M1 times V1 over M2 so starting molarity, starting volume, final molarity, so I've got 2.050 times 30 mLs divided by 0.1025 is 600, but sig digs, I need 4 significant digits, so that's 600 0.0 milliliters. And is that my answer?
No.
Change the liters.
Not necessarily. Read the first 5 words of the question.
Subtract.
How much water must I add to 30 mLs? So 600 mLs is the final volume, but there was already 30 mLs to begin with, right? So to find
We need to subtract the 30
exactly.
to find the actual.
Excellent, good. So 600 mLs minus 30 mLs would be 500 and, okay. So we add 570 mLs of water to the original 30 mLs of the solution. So in other words, you need to be very careful about that word add. So some questions will say, you know, what is the final volume? Others will say, you know, how much must you add? Others will say, you know, if I add this much water, and if I say add, you know, that means the volume is, the final volume is the starting volume plus whatever amount I added. Does that make sense in this question? Hopefully. Oops.
Yeah.
Yeah. It's a very simple thing, but again, if you don't read it carefully, you might have just left it at 600 milliliters, which, again, shows me that you know what you're doing, but you're not being totally careful here. And if you added 600 milliliters, you agree that would be a totally different thing than adding 570 milliliters. So we have to be careful about that.